So again, this is the application of differentiation. Our goal is to find the best box that will provide us the maximum volume given a certain condition, that the cardboard in which this box will be created has dimensions 30 by 30. So as illustrated, we have to cut portions of the cardboard on the sides, and we said that it should be x by x. And with the cutting of those x and x, following the formula for the volume of a box, we have length times width times height, or L times W times height times H. We have 30 minus 2x, again 2x because we cut 2x length on the sides, and then the width is also 30 minus 2x, and that x that we cut will become the height of the box. Okay, so as an illustration, the open box will be like this, where x is the height, the width is 30 minus 2x, and the length is 30 minus 2x. That is how the cardboard is transformed, right? Okay, and then I asked you to expand the 30 minus 2x and 30 minus 2x times x. What did you get? What is the polynomial form? 4x cubed 120x squared plus 900x. That's it? Okay. Please confirm. Did you get the same? Okay. So we have created a function. It's actually a polynomial function in terms of x. So you see the situation, by just using some variables, we can relate all the sides and the height and form a function in terms of x. And x there is the height. So this is with respect to the height. So some people would like change it to v of h, so that we have 4h cubed 120h squared plus 900h, indicating that h is the height. Or you can just use the v of x, meaning with respect to x. Okay, so how do we inject the concept of derivatives in this problem? We have to get the first derivative. So some of you already know the process. Like we have to first find the first derivative. But we want to go deeper into the process. Like, why is it that we are getting the derivative? What is the reason behind? Yes, we know we should get the first derivative, like in terms of the procedure. But why is it that the step should be getting the derivative? Do you know the reason why? Because it's very easy to remember. Just get the derivative. But why are we getting the derivative in the first place? Okay, so let's understand it deeper. Let's start with, or let's continue with a random graph, which is not the graph of the given function. Okay, so as you can see in the graph, there are some points in which they serve as the tip of the function in a given range, or domain rather, okay, domain of x. Other points could be the lowest at a certain portion of the graph, another possible highest point, and then another possible lowest point, right? Although this is the highest point maybe in this area, that is not the highest point of the graph. Actually, we cannot get the highest point because, as we can see, it is indicated with an arrow, so it will continue to move to positive infinity. There are some minimum values, but the graph will move or go down to negative infinity. So technically, there is no lowest value or lowest point in the graph. Okay, so how do we then name these points, being here maximum and then minimum? Even this is a maximum and this is a minimum. These are called, there's a name for this, for these points. These are called relative. Well, in general, extrema, extreme values. It could be relative maximum or relative minimum. They are only maximum or minimum at a given portion of the graph. And it's not only that they're maximum or minimum. There is something about the derivative that is linked to these points. What can we say about the derivative when we relate it to these points? What is the slope at those points? What is the slope of the curve? Or even the tangent line? What is the slope of the tangent line at those points? Your tangent line, for example, in this point should be like this. And that line is a horizontal line. The slope of a horizontal line is 0, even at this point, even at this point and this point. So essential is that those points will have derivative equal to 0. So if we want to get the maximum or minimum value of a given curve, then all we have to do is to get dy over dx and set that to 0. So to those who remember the process, that's always the case, right? Find dy dx and you set it to 0. But that's the meaning, or that's the reason why we have to do it. Because it's only on those values that the derivative will be equal to 0. And those are the points that we can get the maximum or minimum. Okay, so to further or to add more about the terms we use in this application, these points are named as critical points. To be more specific, those values that can have dy dx equal to 0, they are critical points. And specifically, we use the term critical value to specify the value of x. A critical point is x and y. A critical value is the x value that could possibly give us the maximum or minimum. Okay, later on we will see some numbers that are critical values but will not be considered as maximum or minimum. Okay, so critical values are candidates for being or to produce a maximum or minimum value. Okay, so the moment we understand the reason behind, like why do we have to get the derivative, why do we have to set it to 0, then we can just go on with the procedure. Okay, so we will cut it there. So I just provided the base concept, and then we will apply the concept later on in the example. Okay, you can okay, so let me just add to the concepts. By the way, when we look for the maximum value, we are referring to the y value and not the x. Okay, so that should be very clear. Again, if you look for the maximum value, we look for the y value. So in every point, there's an x and y. So for instance, this point has an x and y. So the maximum value will be the y value of this point. The x will only help us determine that maximum value. Okay, so they are critical values. There are critical points, and then finally we have the maximum or the minimum value. Okay, aside from that, we also need to understand that whenever there is a graph, say having a maximum point, it is also best that we understand how is the derivative changing before and after that point. if the derivative is the slope of the tangent line at any given point, then we can expect those tangent lines to behave this way. They are slowly changing in terms of the slope, and then after that point, the slope will change into a different orientation, right? And that the maximum point actually serves as a transition point in terms of the slope. From when we say the slope is inclined this way, that means a positive slope, and a positive slope means that the derivative is greater than 0. If the tangent line is inclined this way, well, we have a negative slope, and this will happen when the derivative is less than 0. And again, at the turning point, which is the maximum or minimum point, the derivative there is equal to 0. So something that we have to note. Later on, when we discuss the first derivative test and the second derivative test, we will be just repeating this process over and over again. And even if the scenario or the problem is different, the process will be the same. Okay? Any questions? Okay. So let's go back to the function that we have. Can you please dictate again the v of x? 4x cubed minus 120x squared 900x. Okay, the goal of this problem was to find the maximum volume. In this case, the y is the volume v of x. To find the maximum volume, we need to find the critical value, and that critical value is the value of x. And that x, when we substitute it to every x here, that will give us the maximum volume. Okay, so this process is what we call the first derivative test. Okay, first derivative test. We will be applying the first derivative test. By the name, it suggests that we only have to use the first derivative. Later on, when we use the second derivative test, we will go until the second derivative of the function. Okay, so how do we apply the first derivative test? Number one, you have to find the critical values. The critical values will be the candidates for the x that could possibly give us the maximum volume. And to find the critical values, we need to find the derivative of the function, in this case, the derivative of the volume, dv over dx, and we want to find those x that will make this 0. Okay? And after that, we will just be comparing. So once you found all those x values, you need to find their corresponding y, and all you have to do is to compare which one will be the highest value. Okay? Of course, there will be tests later on. Will it be a maximum or minimum? Using the concept of the changing slopes. Okay, from positive to negative if it's maximum. If it's minimum, from negative to positive. Okay, so let's apply the first step. Find the critical values. So if v of x is equal to 4x cubed minus 120x squared plus 900x, then v prime of x is equal to 12x squared minus 240x plus 900. And the x that we need will be the x that will make this equal to 0. That is dy over dx is equal to 0. So how do we find the x from this equation? Factor. Or maybe we could simplify first. So all numbers are even, or maybe a higher number can be used to divide these numbers. Can someone check if 900 is divisible by 12? What is the answer? 75? Okay, so every number is divisible by 12 in this. So dividing by 12, it becomes x squared minus 20x plus 75 is equal to 0. And then x could be x and x from x squared. Factors of 75, that will give us 20. Two numbers, when you multiply, the result is 75. When you add or subtract the numbers, it is 20. Negative 15, so minus 15 and minus 5. 5 times 15 is 75. Negative 15 and negative 5 is negative 20. So these are the factors. Okay. So x could be equal to 15 or x is equal to 5. Okay. Now before we proceed, like which of the values should we consider, it is also important to note that the expression came from 30 minus 2x times x before we expanded the expression. Remember? Okay, now, if this is just any function, then numbers such as negative or positive or 0 can be accepted. But the moment you perform derivatives in an application, there are some restrictions to your values already. The length should always be a positive number. Well, technically it could be 0. And then, but they will never be negative numbers. Meaning to say, 30 minus 2x should be greater than or equal to 0, and x must be greater than or equal to 0. Okay? Of course, in this one, we cannot have length to be 0. So we could strictly say 30 minus 2x is greater than 0, or x must be greater than 0. Otherwise, there will be no box that can be formed. Okay, but what will this say? 30 is greater than 2x. So divided by 2, x is less than 15. So if x is less than 15, this is the same as x less than 15. If x is less than 15 and x should be greater than 0, then it means that x can only be between 0 and 15. So it is already restricted between 0 and 15. So even if we obtain x equals 15 and 5, the only possible value that we can consider is x equals 5. Because x equals to 15 cannot be a value. Okay? The process that I perform can be considered as working with the domain of the function in terms of this application. 30 minus 2x should be greater than 0. X should be greater than 0. So that's like the domain of the given function. Okay, so immediately we were able to eliminate one of the options, so the only critical value is x equals 5. But we're not yet sure if this value will give us the maximum, because it could be a minimum value of the volume. So how do we test our x equals 5? Okay, so in step number 1, we were able to find the critical value, and that critical value is x equals 5. This is not yet the answer, but this will give us the answer. Okay, so how do we consider x equals 5? We place it on a number line. We want to make sure that if it is indeed, or it will give us the maximum point, then the slope before the point, the slopes before the point And the slopes after the point should be changing from positive to negative. So the first derivative test will make you investigate what is happening to the derivative before the 5 and after the 5. So how are we going to test that? You will substitute a number before 5. You can choose any number before 5 and then another number after the 5. Okay, suppose we choose 1. Okay, let's go back to your derivative. Derivative is 12x squared minus 240x plus 900. Please substitute x equals 1 to the expression. What will be the result? You substitute 1 in every x here. That's 12 minus 240 plus 900. Without even solving for it, are we expecting a positive number or a negative number? A positive number. Did you understand? So therefore, before the 5, the derivative is positive. The slope is positive, so the curve is increasing. And then after 5, we want to check what is happening. We can use 6 or any other number. And then we substitute again on the given expression. So what will be our v prime of x when that x is changed into a 6? It becomes a negative number. So you can actually get the actual number, but what we want to know is just the sign of the number. So based on your calculation, it will provide you a negative number. So as we can see, we have an increasing and then we have a decreasing, then the 5 can provide us the maximum value. We were able to verify it using the test. That is why it's called a test. You have to verify it, okay, by following a certain process. Okay, but again, this is not yet the final answer. This is just the x. So what then is the maximum volume? So we have to go back to the volume function. Okay, so the volume function, please dictate. Go back to your notes. The volume function is the expanded form. 4x cubed and then minus 120 x squared plus 900x. And then just find volume at x equals 5. So that means 4 times 5 cubed minus 120 times 5 squared plus 900 times 5. Please compute. What is the volume, maximum volume? Exactly 2000? Okay. So the value is 2000, V of 5. So the maximum volume is, if there is a unit, we have inches, right? So cubic inches. Okay. So if they ask, so what is the dimension of the box? Remember, it is 30 minus 2x by 30 minus 2x by x. This is already 5. 30 minus 2x when x is 5 is 20, and this is also 20. So the dimension must be 20 by 20 by 5, and that will give you the maximum volume, which is 2000 cubic inches. Okay, so you don't make a guess. You can compute for the best dimension that will provide you the maximum volume. Application of calculus. You don't do it randomly. It's provided exactly. That's the measurement that we need. Okay, I hope that's clear. That's only the first application, but with that, if you understand that single application, you can answer the other questions even if they change the situation, because the process will be the same. Okay. Okay, so we cut the first derivative test there, and we will discuss in the next part the second derivative test. Okay.